So I have two different presentations here for you. First one is this a new construction high-rise buildings in Kathmandu using dampers, and second one is the heritage building in Kathmandu also, okay, which is a UNESCO heritage building and won the IENA best project of the year, global project of the year. So I'm gonna go through fairly quickly, and I get the question at the very end. Now, can you guys all hear me pretty well? All of you? I'm here in LA, by the way, and what you don't smell here is a nice Indian food smell. I have not able to touch yet. I'll do after the fact. Okay, so let's see here. Oh, there you go. So first one is a new soft story Hilton with the viscous dampers. And many people obviously participate in a project about Dr. Gilani, Ashut, and Sudeep from Nepal office. They're one of the main drivers, and then many people from many engineers from Nepali office. And still, they're actually working on a construction site as today. Now, why is soft story? Because it's not like we chose to make the soft story, but that's how architecturally it was like that. So that's that whole story about how we overcome that. So just back to the 2015 Nepal, they had the two major earthquakes back to back. First one is magnitude 7.8, and next one is about a month after was magnitude 7.3. And Kathmandu, which was essentially right in the middle of between the two epicenters. Now it's pretty far away, several hundred kilometers away for each of them, because Nepal is a pretty big country. However, Kathmandu basin is consists of a very, very soft soil, about 400 meters of the soft clay in it. It's almost like a jello. So it's actually caused a basin effect. And so in Kathmandu Valley, because of the motion, it was a long period of motion, did not affect the smaller buildings because different frequency domain, but affected the taller buildings. That's why when we engineered this new high-rise building, that was the main concern. Because very high, tall buildings, about 3 seconds or so, and it's going to impact tremendously. So 2015, it's affected almost 2.8 million people, killed about 9,000 people, destroyed about 600,000 houses in the whole country, and also collapsed almost 7,000 schools. Now, fortunately, the earthquake happened in Saturday noonish, so therefore, that obviously school was not session. Just think about it this way. If this happened 24 hours before, could probably kill the hundreds of thousands of students. 600,000 houses collapsed. If this happened, say, 8 hours before, middle of the night, I bet you we lost like millions of people, you know? So in a sense, this was a lucky earthquake. So, well, you know, we lost a lot of people still, you know what I mean? But that's a definitely wake up call for all of us. There's definitely danger exists. So in the countryside, now many more buildings in the countryside collapsed because they are unreinforced masonry buildings like this one. But even a place like Kathmandu, you know, many older concrete structures. There's something you see all over the places. There's no ductile concrete structure. Globally speaking, anything built prior to 1980s, even here in California, anything built prior to 1973, they're considered extremely dangerous. Now, magnitude 7 earthquake in Mexico City, which destroyed about 400 buildings and collapsed about 50 buildings in Mexico City itself. Most of the collapsed buildings are built prior to 1985, because that was this whole detailing criteria change after the 1985 Mexico earthquake, you know. So any kind of concrete structure before that era, globally speaking, 1980s is very dangerous. Even new construction. This is the it's completed almost like the same year as the earthquake happened, just a little before. Designed per the latest Indian building code, which is actually a very decent building code, and also the engineer and constructed by one of our top engineering companies and construction companies from India. Even that, if you go see inside, it's become look like this almost not. I mean, this building still unoccupied, by the way, after what 4 years now, you know, and it was a very expensive apartment. So building did not collapse However, this building was not able to provide the occupancy after the major this event. And this is one of the hotels, and it didn't collapse. But when we went in there, actually the Marco from our Italian office went in first. He discovered this twisted, look like a spaghetti. That's it, actually ground floor columns. Can you imagine? So we actually had to ask everybody there. It was occupied, by the way, fully, to evacuate just as soon as possible. The reason it didn't collapse is because of the believe it or not, unreinforced masonry walls above the second floor act as like a deep beam to transfer the loading to different columns. That's why it didn't collapse. It's just amazing, actually. So those unreinforced so-called non-structural walls above second floor, it's very important, you know. Danny knows this kind of story pretty well. Yeah, exactly. So let me show you the displacement motion looked like in April 25th, 2015 event in Kathmandu. You see the strong motion lasts almost like a minute, 40 seconds to all the way to 120 seconds. You can see that. But displacement, it's a 40-inch displacement back and forth, which means 1 meter just going back takes about 2 seconds to coming back. So that's why this kind of motion really affect the taller buildings, not the shorter little buildings. And if you see a response spectrum, it's quite clear. Now, response spectrum is something engineers we use. Looked at the horizontal axis, it's what we call natural period or frequency. So higher the natural period is out here, the taller buildings. And vertical axis is the what we call spectral acceleration, which is the what type of force that particular building taking by the particular earthquake. So see this graph here. In the one building code, one has a complete different, say, shape from an actual earthquake happened to it, right? Actual earthquake, which is that you can see the blue line, it shows the high energy in around from 3 to about 6 seconds because of soft soil. Building code forecasted completely different earthquake. You can see the most of the energy in a shorter period, right? The shorter buildings, essentially, that's what affects to it. So now, Kathmandu site was very peculiar because of what we call base effect, such as soft, deep soil. But things like this happens all the time. It's actually the seismic, this spectra like this. It's almost like a moving target. Building code, size, spectra like this changes every 10 years, every 5 years. So something we're designing today, for example, all the Nepali and Indian engineer thought that was the right shape, but it was completely obviously off. You know what I mean? So anything you design per old code, it doesn't even make sense. The building code is kind of like that. I think that's why it's really important, not only following the building code, but also the kind of follow the physics. What could it be like? You know, you have to kind of think about a little bit more, think deeper. I think that's very important. So here's a challenge. Hilton does a new construction, and it's a 5-star hotel. It's a lot of architectural interesting things going on. It has a roof deck to everything about them. It's going to be 15-story building and 2-level basement, about the 200,000 square feet, which is a 20,000 square meter building, and about over 200 rooms. So this will become one of the major hotel in downtown Kathmandu. It's super critical building. So architectural plan, as you can see, all the layouts going on, and ground floor and top roof. And actually, the middle of construction, the owners, the developers, they change their mind to add 2 more levels on top of it. You know, so we actually re-engineered the whole thing, and we actually added 2 levels by something lighter like steel. But this is actually whole building except for cast in place concrete. Because of that, it's also triggered adding dampers at the ground floor also. Now, foundation system is the concrete raft foundation, which is a mat foundation, about 1.2 meter deep or so, and which supported by the stone piles, kind of, basically packed in stone piles. That's how the standard is out there. And this stone pile is about 8 meters deep, which means about 20 feet deep, and spaced every 2 meters, about 6 feet. So you can see that the whole mat is supported by the big stone in a sense. That's how this whole built. You can see a section of that. And typical floors, you can see that the basement itself are much bigger because parking, all that things going on, and operation components of it. And a typical floor, and there's a mezzanine floor at the banquet floor, mezzanine floor at the lower levels. So have a kind of a complex things going on like a first 3 levels, just like any other hotels you can see like that. And about the third level also become typical, which you can see on the picture right there. Now, when we go to the earthquakes, anyway, actually 4 building types usually collapse, and most dangerous one. Older school buildings are usually dangerous. We saw it in China to Japan to everywhere. Just that reason schools dangerous is usually a pretty large structure, many cases pretty old, and built fairly quickly. In Mexico, we lost some people, there's some kids there in a couple years ago. And classrooms are large and a lot of window. That's why that kind of dangerous buildings. And so school, hospital, because built over the years, this collapse all the time, and church or that kind of religious buildings, because they're usually big dome and big area, and hotels. Because hotels, in many cases, are big concrete structures, have the huge lobbies and what we call soft story, that makes extremely dangerous. So there's 4 building types, So we added 2 levels, medieval construction, man, can you believe it? But at least they told us, which is a good news. So we are able to react to it, and then we added 2 levels of structures up there. It's amazing, actually. Here's a lateral system. Lateral system is a cast-in-place concrete structure, and every column, every bay is a moment frame construction. So it has a pretty redundant system going throughout column space. The spacings are fairly short, maybe 10 meters. Maybe 7 to 10 meter spacing kind of stuff going on, and the big columns. And those red indicates the shear wall locations. So you can see the in y direction per se or transverse directions much stiffer, because you can see the bookend, a big shear walls there, and also in the middle too. But in longitudinal directions, much softer, because we are relying on just basically 2 peaceful shear walls and also moment frames. So that's why we actually provided dampers quite a bit, dampers in this direction, essentially, longitudinal directions, the lower levels. So structural design is Indian building code, which is equivalent to the Nepal National Building Code. We call IS, Indian Code. And also we did a performance-based engineering using the physics, which is this case, we activated ACE 41 to essentially understand what kind of damage this building is going to get and how it can mitigate it. It made a final element like that. Now, one of the main discussion our Nepal team we had with the client basically said, okay, Miyamoto, I want you to design a good building. And I want you to use the latest building code. If you need to be, use American code or whatever it takes to make a good building. But we explained to him, what does that mean? Well, sure, we can follow the building code, but building code is essentially, if you follow it, it will provide a life safety. So which means the building may be occupable, as you saw the pictures in the new building. And they kind of saw the things already, so they understand that the building code has certain limitation to it. You may not lose a person, you may keep it alive, but yet the building may be occupable. But this particular client, they're not on this building for many generations to come, so they want to do something much more than that. That's why that we give them options. We give them options of the using the different technique. So here's the one thing we kind of talk to them about it. Okay, first of all, to get a permit, we design per Nepali code or IS code, right? Which means the member has a completely different seismic input motion, but we designed for that. Then on top of that, we designed for the actual motion generated by the April 25th event. So as you can see, huge difference. That you can see the April 25th motion, which is this one here, versus this building code. If you design per building code, this building only moves only 0.5% of the story height, which means a very small movement, by the way. But if the April 25th event happens again, it will actually move it at 3 times more. You can see that how the code is misjudged that nature is. So we show this kind of pictures. This basically shows the testing done by Facade in LA office in USC. And this is actually the beam column joint, just normal beam column joint, and how actually what kind of drift is it? 3%, 5%? Yeah. So how actually the code means. So we show picture like this, so they can kind of visually see the building code. So okay, we give them an option, right? We can definitely design per code. This is perfectly legal, do like this. But is that what you like? And so no, I don't want that. I don't want to have like that. So we explain what the building code means. Now, horizontal axis of damage, what type of damage, going on, and the number of buildings. If you design per code, it's like this. See, we engineers, we tend to say, if you design per code, you are going to get life safety or immediate occupancy. We make a statement like that. Or we say if you design per code, your building's going to move 1% drift ratio or something like that, right? But it's actually completely wrong. Nature is much more random than that. Nature is not linear. Whatever you're going to forecast, there's a randomness. If I design 100 buildings, exact same way, built in the same locations, and have the one earthquake coming through, you're going to see the linear response. You're going to see the bell curves. Some do perform as we said it does. Some do perform better. Some is less. Because there's a little bit different variation, the constructions and soils and that kind of stuff going on, That's why that we can be so different about what's going to happen to building performance. However, if you do something, like if in dampers and stuff like that, you can narrow the band, which means your certainties can be much higher and damage get less. If you can spend more money, isolation. Now, building isolation, essentially providing the roller underneath the building to elongate the period so you can deflect the earthquake motion. Now, this isolation system like this one will not work in Kathmandu Valley because such a soft soil going on, right? But outside of Kathmandu Valley, it could be great. However, it's much more expensive. That's why people don't use that much. So construction cost. If the code building is, let's say, $100, if you enhance it, enhanced by the dampers and stuff like that, usually we see no more than 1% construction cost increase. That's it. Can you imagine? It's just that only $1 more, and you can make a huge difference in the performance and certainty. This is a reason isolation never been popular in the US. It's too expensive, By the way, in Japan, we have almost more than 10,000 buildings being isolated out there, especially high-rise buildings. California, we have probably like 200 maybe, tops, some on there, maybe less actually. And the main reason is where the Japanese building code set up is their displacement criteria is so strict, actually. If you try to design without isolation, become more expensive. That's one of the main reasons, actually. But also the public are keenly aware the base isolated buildings perform really well. Those things helps, So we input dampers. What does that mean? Let's just give you some dynamic equation. So earthquake motion, how much is going on, expressed out here. Acceleration times ground, That breaks down to 3 different energy components. One is a mass, which means like a floor acceleration going on. That's the energy breakdown. And other energy breakdown is the actual displacement of a motion itself. That's how we engineer buildings most of the time. We look for mass, weight of buildings. We look for stiffness of buildings. That's how we engineer it. Many cases, we use this is dampening CV. Dampening components, essentially, we just say, 5%. And in the US, we change to maybe 2% or, that kind of things. And globally, people use a 5% damping ratio. What does that mean? Well, things breaks, things fall off, this light's coming down, all kind of stuff happens. So that damage, architecture damage itself, causes a so-called damping effect. That's what we call them. dampers do is artificially create this C constant. So make this damping constant much bigger, not a 5%, talking about 10%, 15%, 20%, big number. So therefore, the other components get less and less, you know? That's how we actually control the ground motion. So this is what it look like. And it's essentially look like a brace. And this is one of the buildings in California, actually. If you cut section that, it's look like it's actually the look like it's a shock absorber, but kind of big. It's not really expensive. Usually about $3,000 US to maximum maybe $10,000 or so. And if you even have a 20 of them, if you see the whole building, it's very small amount of money. Now, this is actually what's made of the stainless steel and has two different chambers, as you can see. And it's a pressurized vessel. At rest condition, about 2,000 psi. And when the earthquake hit in it, it will basically push the one chamber. It's compressed. It goes up to almost 10,000 psi. And the fluid, which is silicone oil, going through the orifice around the cylinder head, about speed of sound. So that causes the heat and dissipates it into air. So that's the whole concept. Earthquake energy convert to heat energy. That's what viscous damper is about. Now, this kind of devices actually is a perfect for condition where we can control the actual period of a building and strength of buildings and stuff like that. You know, it's not for everywhere. For example, if I have the very brittle, weak, like a non-ductile concrete structure, really weak one, and has like a not much understanding of what's inside of it, using viscous damper itself not going to work out so well. You're going to have certain stiffness, strength, stiffness to that. That's why that we, many cases, we use buckling restraint braces because it does provide the stiffness and strength to go with them. So here's damper locations. You can see that everything on a longitudinal directions, like a 4 locations, and we only put that at the first 3 levels because that's where that kind of soft story thing is going on. So you don't have to provide dampers everywhere. Just provide a damping devices where the maximum displacement is, highest velocity is. It's a velocity dependent devices. So like that, you know? And it actually, it's under construction right now. And they actually did order the damping devices and they'll put it in. It's just pretty amazing actually, which is incredible to me. So here's a performance difference with and without dampers. Without dampers is a solid line and an X and a Y direction. And with dampers, you can cut down quite a bit. Almost about 30% difference at the top of a roof. If you see from a floor to floor, this is how we engineers, we kind of gauge the building performance, drift ratio, which means the percentage of movement of a building. Let's say that if you got 100 centimeter, if the story moves 1 centimeter, it's a 1% movement. And generally speaking, building system, if you can keep less than 1% of drift ratio, performance is pretty good. Even some of the brittle elements in the building, performance is actually very decent, generally speaking. So if you're shooting for some sort of a good target displacement or drift ratio, 1% is one we try to usually use. So this case here, that's exactly the whole concept. So let's see, at X direction, which one's weaker? X direction. X direction is weaker, which this one here. So had about 1.5% drift, you can try to reduce to close to the 1% as much as possible. That's what we do there, essentially to control the damage. Same thing applied on the Y direction, which is much stiffer one. It was over 1% down to about 0.9% range. So this is actually damage control methodology, just focus on displacement. So somebody asked me, would you use the R factors and all the little factors, different countries have different code, different factors? No, no factors at all whatsoever, one. And you actually run the real analysis into the real nonlinear environment. That's what we do. See, this is dampers in one of those buildings. Isn't that kind of cool? It can be really cool things, man. I told you structural engineering is cool and sexy. Am I right? See, this is one of the buildings too, in Sacramento actually. I love this architect. They put actually inclined table, exact same incline of this. Genius architect, I don't know who was. So let's see. What am I looking here? Oh, yes. It's an animation difference. So you can see the kind of shadowed up, kind of, you can see difference of movement before dampers and after movement. Can you see it, Miguel? He said he cannot. Yeah, exactly. Watch carefully, the punch. And the construction started. It was about almost a couple of years ago. And right now it's top off to about 15th level. It's a concrete finish. But it was a pretty nightmarish. I mean, it's you know what it is? It's a landslide. So they actually built, digging a big foundation, right, in the middle of winter. It was a rain coming through in the Kathmandu Valley. And they decided to expand the building. So they kind of left this site like this for a little while. And one day I got an email call from contractors. Hey, there's a landslide, building site. Anyone got injured? No. Good. Let's fix it as soon as possible. Yeah, it was pretty intense. But actually, it once go up to the upper levels, construction quality become pretty good. It's you can see that the good detailing technique they use. 50% completion. This is about 6 months ago. Right now, it's at the 15th level today. Just go up to the what's that called? The steel level. Shear water bookends. Column reinforcement. Columns are rectangular because try to match the width of this wall much as possible. That's why that is so-called long-term directions fairly much softer than the other directions. Formwork placement for some concrete. Now, how get a permit? So Nepali government use a very rigorous approach. They hire the peer reviewers and all that stuff to kind of go through the whole approval process of it. But when we go through this, pretty much it's true for every country. We design everything per minimum this local code, so it meets the minimum code. Then we apply the damper devices after the fact. So you don't have to really get into them much. That's actually the approach about them. Now, I think that the US and Japan's only codes I know actually using dampers, you can reduce the amount of steel. For example, the ASC7 allow you to use the using dampers to reduce the actual or elongate the period, reduce the amount of stiffness. So for example, we actually looking the Connextech is one of a steel fabricator system provider, like a big moment frames they have. They try to reduce this tonnage. So we are using dampers and then keep the kind of close to elastic level, but they are much less amount of steel. So we are looking at the cost reduction measurement and plus enhancement of performance. That's what we're looking at. Way back when the in a medical office building for Saddle Hospital we did in Stockton, we actually at the pin at the bottom is moment frame construction. So we eliminated all the gray beams. We put dampers at the gray. We actually create a soft story intentionally. So you can do things like that. The reason that we have a higher confidence is because when you put damping devices, you keep remain elastic, well, really close to elastic response. You don't really rely on the hinge formations and that much. So that's why that you have a much higher confidence in the design actually. And rigorous construction quality by the owners, engineers, and government. Next year should be look like this. Isn't it cool? I think it's fantastic. This is definitely at the first building in that particular area, Nepal and the whole area to have this kind of building system. I think it's fantastic. So next one is change the gear a little bit. It's an old construction. It's about 120 years old building. Repair and strengthen the earthquake damage UNESCO ancient palace in Kathmandu. And Dr. David Sonda from Italian office and Ashu, they're one of the main drivers for engineering. And also Ginny and Sabine Cast from international development, and they're a really big part of it to get things done because this is a we have to go find money to get funding actually because when we found this building, it was a pretty bad case. But this was a neoclassical style being built in 1907. Historically very important. This is the middle of Kathmandu, right center of it, place called Darbar Square. And it's, as you can see, it's a beautiful building. And it was a foreign dignitaries being accepted, and it's a guest of a kind of place. So it was a very historically very important place, and it was a symbol. But after that 2015 earthquake, become look like this. And when we go through the whole buildings, it's abandoned for 2 years. It was a horrifying condition. And at the time, one thing we noticed that many of the heritage buildings lost, they're taken down. Some cases we thought there's no need to take it down. Some even little cracks, they take the whole heritage buildings down to build this kind of modern, ugly buildings, you know. And Kathmandu, or any other places, heritage building is so critical. It's a really not only history but culture of this whole people, you know. Everything's in there, so not easy to take down. But this particular case, pretty bad, I must say. Out of plane collapse, columns are tilted, and some of the local structural elements. Fortunately, inside, damages was somewhat limited, you know, like that. But after 2 years, it was absolutely looked like this. By the way, guy at the corner is not a ghost, it's Ashut, the engineer, right there. I want to make sure you know that. Actually, this building is something Ashut. He was our chief engineer in Kathmandu office. Now he's a corporate engineering team in Sacramento today. And this was one of his master thesis, you know, way back when for seismic strengthening. So we had a pretty decent knowledge about it. So when we found this thing, essentially the devil would abandon this building. There's no way people said, we're going to fix this building, we're going to take it down, we're going to do something about it. So we just said, no, I don't think that's a good idea. I think this is such an important building, we can do something about it. But there's no money. So what we done is Miyamoto Relief stepped in. Miyamoto Relief is a non-profit. You know, for the business like us, Miyamoto International, we have to follow somebody else's strategies, right? You have a client, you're for the client. Client said you build, you build. Client said you fix it, you fix it. But non-profit, we have our own agenda. We are the client, we look for money. So Miyamoto Relief, what Ginny and Sabine's team did is they look for funding, and they found one. Well, first of all, it was actually a pretty long process. You have to go through the approval from a Department of Archaeology in Nepal to convince them, say, hey, we can do something about it. That itself, like, I think Ginny spent like 1 year to just convince just doing that, right? Then the UNESCO is also the UN agencies you have to deal with. I mean, they're definitely for that. Then we went to the US Embassy. There's the funding called the US Ambassador for Cultural Heritage Preservation. And they actually funded almost $700,000 for this. And even students, this is Cal Poly, California Polytechnical University from California, San Luis Obispo, and they have the student group called SESH, that Structural Engineering Students for Humanity. They have this organization for almost it's probably almost like 8 years now. And every summer, the students, they actually raise money, they come to collaborate with the Miyamoto Relief. So this particular case, they raised $10,000 actually to basically get the uses of funding for this part of it, renovation. Isn't that fantastic? I think it's just great to, fact is we can, you know, energize other people, young people, you know, all the people to actually do something about important to the society. I think that's something that our company is very special to me, you know, it's really cool. So those guys done actually quite a bit. They camp out for a whole week and they did a detailed damage assessment with our Nepali engineering team and the map, all the cracks, everything about the whole building site. And some of the damage we saw, well, some of the things we found, like a masonry wall. It's mainly made of a mud mortar, but there is the actually layer of a lime mortar also, kind of combination. So Because when we go to a UNESCO building like this one, you cannot just kind of bring in something don't exist. You have to use whatever it's there. You have to respect the heritage of how they built. So that's actually one of the most challenging components of it. That's why we can do like dampers and which technically doesn't work anyway, but it doesn't quite work. So we need to use some mud, lime, mud, and brick. Timber, there's a lot of wood on ceilings and all that stuff like that. They're actually fairly decent condition. And we found some steel straps. Some of seems like they added after 1934 Kathmandu earthquake. So we know that steel, some part of straps like that we could use. Tin, and a lot of our architectural heritage elements made of tin. We find a lot of those things. So those are things we can use: mud, brick, lime, tin, some metal, timber. But believe it or not, what Dr. David Sonda and his group did is make those things to not only respect the heritage elements, they make it actually better than what would have done. Actually, let me show you how. So first, the group made the finite element like this one. Then try to understand what is the actual building characters look like, and then try to compare against the actual observed damage. So this building has about 1.33 seconds or so, some in the range. Now, this is actually pretty bad because as you know, this Kathmandu earthquake, remember, that area, 1 second, 2 seconds, 3 seconds, they're like a really high energy bad area. You want to avoid to, but that's right in there. So one thing we know, we need some stiff in this building a little bit. So going through all the stress, checking all that, we're looking about the 1.8% drift ratio, 2% drift ratio, which means that if the building height is 100 centimeter, means two centimeter movement. So it's a pretty healthy movement, like you can see. And columns tilted, we forecast about 180 millimeter. We measure it on the side. We're correct. We moved about 195 centimeters. We didn't measure this. We analyzed first. I think. But it's a huge movement. 1.8% is a huge. 1.8% movement is a big for like say this building you're in. We're gonna say huge amount of damage, but 1.8% is a gigantic number for the historical building, like especially made of mud and brick. So no wonder there's a whole bunch of damages in there, and the stress ratios too, pretty big numbers. Some of compressions like a demand capacity ratio of 3s and stuff like that. It's a big numbers. So first option, we kind of thought about it, is use the modern construction material, concrete, steel. We do that in California, right? You see at the URM, unreinforced masonry buildings, what we do, we put some steel braces in there. We think it's gonna work. Italians find didn't quite work. This is one of the pictures Davis and Marco, an Italian office, took. You can see the kind of steel cage back there. That was a seismic strengthening elements. Because what it is, and actually I see things like this often too. If you just think about it, you got the pretty weak brick mortars, that kind of things going on. You're gonna add something very strong stuff, big connections and epoxies and stuff. Look where the failure mode is gonna come from. Somewhere strong, So we gotta be careful about, sometimes put too much stuff, too much strength, doesn't mean it's better, So no go for option 1, especially that it's not allowed by the UNESCO to doing things like that anyway. So option 2 is enhancement of original construction technology. Understand the original traditional system. What does this mean? How actually survived through 400 some years. They went, it did went through 1930s earthquake, didn't collapse completely. And understand why and what went wrong in this particular event, and follow the original traditional system. Keep what worked well, and retrofit the cultural and history. So here's the kind of a system it look like. You're looking at plan view, which means looking from above. And like this is a red big box. That's the kind of a strong stuff. That's a kind of full, this tower, big, thick brick components in it. So that's one, we know pretty strong stuff going on. And a green back wall, that's a long wall. Sure, made of a brick and a mortar, but this is a long, long wall. So pretty strong on this direction. And the blue components down the bottom, that is actually the wood the half rotten wood thing. So you can see that it's kind of there, but it's not really provided any what we call integrity in the whole system. It just everything kind of could have fallen apart. Sure enough, damage is observed in those places. Damage is observed in these three big corners because they're pretty stiff, cracked heck of them, and this diaphragm in the middle, which is swinging back and forth, that made a huge failures. That's what we see out there. That's a little diaphragm components of it. But that little piece actually very important because that little piece actually tried to stabilize this out, the facade column. Somehow need to tie back to this column want to come off. Somehow tie back to it. That's what's going on out there. And joint between at the roof truss and the brick, there's some certain damages obviously because there's no good connections and stuff like that. So here's what the math models look like. You look in the section view. K1 is at the little stretch of this, the diaphragm I was talking about. That's actually trying to stabilize it. And K2 is essentially trying to connect this, connect the between the this big truss, essentially try to connect it. And K3 is actually donut, kind of a diaphragm. We try to create them. So we try to create the three different stiffness or strength or connections. K3, little donut, above ceiling, by the way. K2 is a truss. We connected everything together. And the K1 is the long piece of a front one. So all the K1, K2, K3 work as a one unit, essentially, try to stabilize the whole thing. And this is something that what the Italians do really well is a rock analysis. So they see see in a like place like California, we see this wall to be like some sort of concrete, but it's not. It's actually that the whole thing is rocks. Whole thing could be breaks in the middle, could be rocking back and forth. It's a stable motions to it. So David Sonda and his group has this software they developed. They analyze the rocking motion of a system like that. So that's how they analyze the whole building. As a brick itself, you model brick by brick, you're rocking around, you connect with a certain stiffness. And what's the best stiffness out there to make this more stabilized? So here's what it look like. K1 is the, what's K1? K1 is the front one, right? That's what it look like. So made of wood, this is what it look like. You know what I mean? Just a little piece of wood to make this K1 components. You can see the section view there. Heavy timber construction. Then restoring the improvement, the truss wall connections. So there's a truss itself connected into that. So that itself is one of the key elements. So connected, because you need to connect to two walls. Now, first, David Sonda thought maybe he will connect this with the rod. Now, if you go to Rome, you go ancient cathedral. Sometimes you look up, you see a big rod. That's what those guys try to do. Essentially, what rod does is this wall want to come off. Well, if you got a rod, it can come off, right? Because this is going to be try to come off. This is going to be butt into the roof itself. If you try to go this way, it can't go neither. Other way around. That's what the whole rod's about. So next time you go to Florence or Venice or Rome, you can see at the rods. That's what they're doing there. I think that's such a cool idea, by the way. It's fantastic. So here we try to do that by the actual truss itself. You can do the same thing. Then on top of that, provided the band, this donut diaphragm around it. So three ways. Detachable band diaphragm. This is made of wood. First time when I saw this plan, I called Davis. Say, hey Davis, this looks kind of weird. It's a wood. Usually we use steel connections and that kind of stuff. He goes, well, number one, it's prohibited. Number two, that's a really bad idea, kid. You want to make something soft, something weak, connect together. That's actually making so much better performance. And he showed me those pictures, That's so true. Then obviously locally you need to do certain things, proper reinforcement. But proper reinforcement, it's not done by steel, it's wood. Soft. Energy dissipations, that kind of things. So critical. Then we use the steel rod at this corner elements to connect together essentially. So the steel rod is embedded into the brick itself at the four corners. just tensioned in, essentially. So act as a one big unit. Then some of the big columns provided the steel rebar, some straps, stuff like that, stabilize them. And here's a repair methodology of the broken bricks. Just try to use the original, salvage the original available brick much as possible, kind of build back exact same way. And the lime mold is a mix with the lime also, so have certain cohesiveness in it, just not only mud. Build up like that. Then wood band. It's providing a wood band in the brick walls. That's something that you see quite a bit in a place like Nepal and India. And it's actually performed very well. So provide a band in a system like that. And in a connection of a brick, that engagement is a very important one. Now, what blessed here is the craftsmanship of the Nepali contractors. I mean, they're fantastic. They preserved all the knowledge of how to do it. And because they do have a lot of heritage buildings, they use the technique all the time. So they do fantastic projects. So after we done all that, what happened to it? Well, drift ratio, remember, used to be 1.8%. I said too much. Now went to the less than 1%. Remember, we're shooting for less than 1%, 0.84%. And displacement of column reduced from the there was 180 millimeter, something like that, to down to 74 millimeters. So it's much stiffer. Then stress went down from compression from a demanding capacity ratio was 3 to down to less than 0.87. So here's it look like. Drift ratio went from 1.8% to 0.84%, make much stiffer. And the compression stress went down from 3 megapascal to 1.7 megapascal. That's within allowance. And the shear stress in the parapet is 0.6, 0.3, same thing. So everything kind of kept to remain elastic state. So here's what the before and after picture. You can see how much moves. In the black one is before. You can see that all the damage caused by this such a huge movement up there. But because it provided a new diaphragm, new connections, new ring thing, stiffen the whole system out, and the strengthening of a corner elements essentially. So it was like this when the construction started. Isn't that cool? Those guys did such a great job. Actually, the permit process took us almost a year. Construction, it's a blistering fast. It's like an 8-month period. They just kind of just knocked through the whole things out. They did a beautiful job there. And obviously, Nepali office participate this rigorously for construction quality assurance. We have a full-time engineer assigned to the site. And they did a great job. Parapet reinforcement. This is the wood band built inside a brick wall. Look like that. And inside, reinforce the columns. Reconstruct some of the columns because it's so tilted and damaged. Some craftsmanship to restore the all those ornamentations. It was a fantastic work, man. It was beautiful work, you know. And what is actually really cool about it is it was a construction project which everybody completely thought it's not possible. But the Myanmar Relief, Ginny and Sabine and those people, they had a hope. They got a hope we can do something about this thing. You know, we connect with our Italian experts who done things like this before, you know. And all together, we actually made this happen. And this is a project which I do feel we gave a lot of confidence in the nation of Nepal about we can restore the buildings, we can restore the Kathmandu, we can actually reconstruct, you know. So that's why that they got a huge attention from Prime Minister to everybody, to ministry, to came to the inauguration of the building itself. And as many of you know, NGM News Record identified this building to be the best global, one and only one project in the whole world of the year. Isn't that amazing? That's pretty incredible to me because this project is pretty small, right? $700,000. something like that, compete with this humongous, like $1 billion construction in Qatar or somewhere, So that's why it's so cool about this project. Cool about this is that we're able to connect different expertise and passion from different parts of the world. And we identify the project needs for the people in Kathmandu. We identified at the US Embassy the funding source, and in Cal Poly, we connected that to make this happen. So cool, I'm so proud of it. Muchas gracias. Thank you. Unbelievable, 110 slides in 55 minutes. So, anyone questions from either LA or anywhere in your office? Anywhere? Yes, Fasi.
I have a thanks for the presentation. I have a question about the first project. What is the problem of base isolation and stuff?
His question is Fasi question in LA is for the Hilton project we worked on. What is the issue of a base isolation? Why cannot use a base isolation? Right? That's the question. On the soft soil. Well, because of resonance effect. Because the whole concept of base isolation, because base isolation can kind of come from the New Zealand, California, Japan, like that, where the muscle motions are fairly stiff per se. Well, high frequency motions. And so you got a motion, high frequency motion like that, like LA, most of motions kind of like that. You wanna isolate the building from away from a certain frequencies. So if you isolate from move that frequency far enough, doesn't even feel them. For example, many earthquake, this building we're not gonna feel it. We in a 60-story buildings. This have a probably period of like 4 seconds or something like that. It's a 1970s steel construction. You could say dangerous, but it's in a sense, it's a period is so high out there, this is not going to feel. Many earthquakes do not even, it's an isolated motion. It's kind of like that, right? So like a base isolation in California really makes sense. Usually isolation bring the period, it's a typical stiff building, about maybe 0.5 to 1 seconds to all the way to 4 seconds, some cases even 5 seconds. So it's going to really, it's isolates essentially. The problems of Kathmandu is because soft soil. It's a 400 meters of very soft clay. So that actually the motion itself is 3 seconds motion. So if you try to put the 3 second motion on 3 seconds, it will cause much more damage than you can imagine. That's why you don't want to use the base isolation of soft soil.
And then 1% difference in construction costs.
Yeah.
Is valid for the United States or like is valid locally?
1% construction cost difference is the US or any other place. It's pretty much valid throughout. I mean, yeah, it's a construction cost obviously varies, but even the Kathmandu project, it's not a huge amount. If you look at total construction cost, it's just not a huge amount of cost at all, actually. So question is a 1% is it true? Some country 0.5%, 0.3%, some country maybe 2%, some of the ranges are plus minus, But this kind of system we're able to use everywhere, from Haiti to Nepal. Those are one of the poorest countries. So sure, you can pretty much use it any place in the world. But communications are one of the most important. How to communicate to clients, give them more options, give them what is the performance means in the building code. Do they like it? If they like it, that's okay. I think that's a really important aspect of it, to communicate that. Any other questions from anywhere?
This is Sanjay from San Diego.
Yes.
One question I have is, looks like for the restoration project in Kathmandu, the materials you guys were using were very atypical, kind of, the mud mortar and things like that. Did you have to do some intensive testing to get material properties, and how did you go about that to model into your, to model properties into your models and things of that nature?
Yeah, we use definitely the so-called atypical in a sense, in the California sense, definitely atypical. We're not going to use mud here, but mud mortar and lime is used throughout the world. It's actually commonly used in Nepal, even today for new construction. And so there's a lot of understanding of how the mud motor works. And um, for example, Jitendra from our New Zealand office, his PhD is based on that, just using a whole bunch of testing of the how the mud motor construction works, small buildings works. There's plenty of research out there about the mud motor and lime interactions and all that stuff. So we use a lot of research data from past, but also same time we done a lot of testing on the site too. A lot of things. Any other
Kit,
questions?
I have a question as well. Zach
Who's
from
this?
San Diego.
Hey, Zach.
Hey, it's a two-part question. One, for the Hilton project, did you guys perform a site-specific hazard analysis, especially considering the effects of soft soil and soil structure interaction?
For the seismic hazard analysis. So essentially, did we do the seismic hazard analysis to see what kind of ground motion is? No, we didn't, because there's no available data out there. There's nothing out there. So basically, what we done is best available informations, which means essentially one is a building code motion. We have that. Second one is what happened in April 25th motion. We have that too. That's the only best things that are available at the time. So that's the two motion that we used it. You know what I mean? Is it the next earthquake will be quite a bit different from the April 25th? Potentially, and potentially bigger. If the epicenter is closer, you're going to see probably the different kind of things happening. And the frequency content can be different though. But one thing about Kathmandu Valley, or 400 meters of the soft soil thing, it's like a whole basin is almost like a base isolated. You know what I mean? So somewhat the predictable what could happen to that. It's a really rare case. Something you may see in Reno, Nevada, similar kind of things going on, kind of basin effect could happen up there, and then we saw obviously Mexico City for sure does have the soft soil of about 30 meters or so. That has the profound impact. It usually doesn't impact smaller buildings and taller buildings in Mexico City. So no, I think it's just that some cases just don't have enough means to get the more analysis, the more testing. Just use the best available data to just provide the most redundancy to it. Remember, whatever you're going to do, probably wrong anyway. Whatever analysis testing you do today would be probably outlawed 10 years from now. I think one most important thing is to provide a system which has can take the many different kind of motions. You know what I mean? Like one of the heritage buildings we did, I like that what they did. Just a lot of a redundant system about it. I like the Hilton thing. A lot of redundant shear walls and moment frames and on top of the viscose dampers and stuff like that. Viscose dampers is essentially those things are really frequency independent almost. It's really take care a lot. It's a velocity dependent devices, so it takes care that any kind of motion coming through to that. And then good detailings. I think that kind of things that are extremely critical. I do think. Spending more time in detailings, spending more time in thinking about it.
Can I ask my second question as well?
Yeah, Zach. Yeah.
Yeah. Did you say that you only used that one ground motion record, or did you do a whole suite of ground motion records? And if you did you consider more than just the first translational mode, or was that mode considered dominant and all the other modes were not? In which case, you would not have to scale your ground motions for different spectral periods.
Now, remember that the Hilton building is essentially the design per code for the whole frame itself. You know what I mean? You're adding dampers to it. Now, we have like 3 different ground motions we usually use. Now, like for example, LA office just engineered the building in San Manuel, right? That case, we use how many ground set of motions? Not 7 pairs of time histories. I mean, the reason we do seven set of time histories is because of the many cases we have no idea what the frequency content is. I mean, like my thesis, I use like a 40 sets of time histories to run through the whole things, right? Because we don't know what we're talking about. We don't know what's coming. That's why you want as many different set of time history much as possible. That's how we kind of do things, kind of randomness about the whole input motion. You take average and that kind of stuff. But since Kathmandu Valley just doesn't have a case like that, that's why we basically use like April 25th and some of the synthesized time histories, that kind of things. That's what we did there. I think I think a new building code to change it probably shape of the response spectrum a little bit. to a little bit more of the high energy content in at the longer period, a little bit out there. So which gonna basically whatever they're gonna do now, it covered by that all the ground motion we use, put this way. Any other questions? Yes, proceed.
Regarding the Kathmandu
Yes.
heritage, okay, so the period of the structure reduced to point 0.8 from 1.8, right? So, so when the period of the structure reduces, you absorb more energy from earthquake, right?
Now which one which building?
For heritage,
Heritage building.
yes.
Yeah.
Yeah. Okay. So the building absorbs more energy. Uh, have you considered the foundation too? Like, is there any specific consideration for the foundation system to take that extra load,
Mm.
or it was already strong enough?
Yeah. No, actually, it also Zach asked the same question. We didn't answer that. The foundation interaction components. I think actually we ignore the foundation interaction components of it, and that's actually the more conservative though. This particular case, because we got the basement, we got the two levels of basement, and there's stone columns down there, and almost what I said, 70 meter, whatever, some So it's pretty rigid base we create them, but there is a quite a bit interactions from this basement structures to the soil itself. It will absorb the humongous amount of energy actually. So I mean, used to be, I remember that I was talking to Dr. JP Sin a while back, and his opinion, most of the buildings should be collapsing, but because of basement, because of soil structure interactions, soil structure interaction actually save all those buildings, Because if you design as a fixed space, it's very, very conservative, actually. And in some cases, you really miss the whole point, especially if you got very rigid construction. If you don't model the soil structure interaction, it's very difficult. San Manuel, did we model that? I don't remember.
No,
Yeah, yeah. But you got a piles though, right?
it was
Oh no, we got the yeah, yeah. If you got piles and stuff like that, they become pretty stiff actually, you know. But depends on how much do you want to model this thing. You can model everything, right? I mean, you never become right. How much on the effort you going to spend on the modeling? I think that the really important thing is that you need to understand. You got to come to your engine judgment. You need to understand. You get to do your engine judgment based on the past experiences, past failures, or observations. You know, your brain is so much better than a little computer analysis. In a building code, become complex and complex every year, right? I mean, it's just nowadays it's incredible. When I was in AC7 seismic task committee, it was crazy. 60 people in there. Today, even me participate today. 60 experts like us. We take a votes. And I remember one year we decided to write a commentary, but all was forgot. Some of the things come from. We don't remember why those factors in there. It's a building code process kind of like that, you know. And building codes is kind of like that. That's why that's a very important. I mean, analysis is important, no question about it. But understanding the whole physics, understand the engine judgment, to understand from past observation of it is critical. You know. Any other questions besides Fasid and Zach? Just kidding. Sounds good. All right. Well, guys, any other questions? Personally, whatever, just email me or call me up. All right. All right. Thanks so much.